Section 5.4 has to do with the graphs of sine and cosine functions. It might be a good idea a few points throughout this video to pause the video, write down everything that's on the screen, and then replay the video so that you can pick up what we're talking about. So to start, we're going to look at two different graphs, just our basic ones. We'll get into more complex ones, other graphs of trig functions as we move forward. But I'm going to start by writing out my parent function of sine and cosine. Those transformations that we've been applying to all these different functions all year, we're going to keep applying, but now to sine and cosine. So the key thing here is learning your sine and cosine parent functions. So you might want to star this, bold this, put an arrow here, because you need to memorize these. There's actually going to be a quiz that is just giving back your sine and cosine parent functions. So to start, we're going to look, a sine curve starts at 0, 0, and then pi over 2. We're talking about 1. At pi, it's 0. At 3 pi over 2, it's negative 1. At 2 pi, it's 0. Notice my graph is in radians. So again, we've been stressing the radians versus using degrees. The reason is that we're only going to be using radians now. We're not going to go back to degrees. So if you haven't learned your conversion, the more practice you can do, the more comfortable you'll become with it. These values from this, or for the sine and cosine curve, are derived in 5.3 in example number 3. If you look back at 5.3, example number 3, we looked at our quadrant angles, and those were nice, neat values. This is going to be way easier to graph 1, 0, negative 1 than it is to graph radical 2 over 2 or radical 3 over 2. So we're going to look back here and just sketch our nice sine curve. So what's going to happen is I'm going to put these points. I put a point at 0, 0. I'll put a point at pi over 2, 1. I put a point at pi, 0. At 3 pi over 2, negative 1. And at 2 pi, 0. So I've created this, it's going to curve, remember, and then we've looked at this graph before. It's going to bounce up and down between 1 and negative 1 to infinity on the right and to negative infinity on the left. So I'm going to start, I want a nice smooth rounded curve. So it's going to look something like this. I know I missed a little around at 3 pi over 2, but just do your best, make it a nice smooth rounded curve. And you can see I spaced out my graph here by doing every 3 spaces was half a pi. So 3 spaces, pi over 2, 3 spaces, pi, 3 spaces, 3 pi over 2, 3 spaces, 2 pi. In some cases, it's going to take some planning in advance to figure out how much space you have and how much you need to show of the graph. Cosine, the graph starts at 1. So my points are 0, 1, pi over 2, 0, pi is negative 1, 3 pi over 2 is 0, and 2 pi is 1. Again, it's going to bounce between negative 1 and 1. So I'm actually going to come from the down and hit that point, and then here, and go back down. So that would be my cosine parent. This is one little chunk. We know that after 2 pi, the graph starts repeating and the circle starts repeating. Your unit circle, 2 pi is the same thing as 0. So it's just a coterminal angle. If I pick this graph up and repeat it, I'm just going to be graphing all my coterminal angles. But the graph goes on for forever. I can make that circle go around and around and around. That's why I'm looking at one chunk from 0 to 2 pi, because after that, it's just repeating. Those are my coterminal angles. They're just showing up again and again and again. Except we don't know the difference when we look at it on the circle unless it's been drawn in for us. That example of 10 o'clock in the morning or 10 o'clock at night on a regular clock, you don't know the difference. So here are transformations we're going to apply. Note that sine can be any trig function here. So I use sine, but you could write, we can do a transformations with cosine, with trig, with cosecant, with secant, and with cotangent. So moving up or down means we're adding or subtracting after the function. So if you see f of x equals sine of x plus c minus c, the plus means up, the minus means down. We take those as they are. A number out front is a vertical stretch or shrink. If the number is greater than 1, it's a stretch. Remember we watched that Harry Potter clip and it says, why the long faces? A number greater than 1 is going to make your graph tall and skinny. A number between 0 and 1 is going to be a shrink. It's going to make your graph short and fat. It's going to flatten it out. A stretch or shrink horizontally is happening inside the sine function. This is the only one we haven't really looked at so far, but this is the opposite. So a is greater than 1 means we're talking about a shrink, whereas a between 0 and 1 would be a stretch. Next is a reflection. A negative outside of the sine function, right here, means it's a reflection over the x-axis. We're negating the y value here. We're negating the entire sine function, as opposed to f of x equals sine of negative x as a reflection over the y-axis. We're just negating the x value here. And then our last transformation, f of x equals sine of x plus or minus a. Notice the transformation is inside the parentheses. So it's the opposite of what you would think it would be. So a plus is to the left and a negative is to the right. Again, these transformations we've been working with all year. We're trying to hammer them home and apply them in all our different chapters. If you still need to learn these, you need to put your nose to the grindstone and learn them, because otherwise the rest of chapter 5 is going to be brutal. One cycle of our graph, like I talked about from 0 to 2 pi, is called the period on the function. The parent function, the period is 2 pi. That's one full rotation around our unit circle. Essentially, the period is how long it takes for the graph to complete an entire rotation. Manipulating the graph by horizontally stretching or shrinking changes the period of the function. So I highlighted that. I would also, if I was you, highlight that. So the definition of a period, let p be a positive number. The period of y is equal to sine of b over bx, and y equals cosine of bx, is given by period is equal to 2 pi divided by b. So when we're talking about b as being equal to 1, we're talking about one rotation. Then 2 pi divided by 1, our period on our parent function is just 2 pi. If we stretch or shrink the graph vertically, we're manipulating the amplitude of the graph. The amplitude represents half of the distance between the max and the min. So for y is equal to a sine of x and y is equal to a cosine of x, the amplitude is a. If you look on our parent function, the amplitude is 1. And if you look at the entire distance, it goes from 1 to -1, which is a distance of 2. My amplitude is basically how far from my center I've traveled. If this is my center piece, this is what everything is cutting through to get to the top and the bottom. It's 1 up and 1 down. So my amplitude here is 1. We're going to look at other graphs that are stretched or shrunk, and we'll have different amplitudes. So this example 1, says on the same set of axes, sketch the following graphs. And it gives us y is equal to 1/2 cosine of x and y is equal to 3 cosine of x. So to start, I'm going to sketch my parent function for both of these. Just start with my parent table, because I'm going to make transformations to the table before I try to mess around with the graph. So I'm going to write my parent function for cosine. Which, if you need to go back and look, go back and look. It starts at 1, so it's 1, 0, -1, 0, 1. If I have a 1/2 out front, that is, based on my transformations up here, a stretch or shrink, and the 1/2 means it's going to be a shrink. So that means to my y values, because it's a vertical stretch or shrink, I'm going to multiply all my y values times 1/2. And that's because this is a vertical shrink of 1/2. So to do that, I'm going to keep my x values the same. I didn't do any horizontal, which would be x value transformations. So I keep my x values the same. 0, pi over 2, pi, 3 pi over 2, and 2 pi. But I did do a vertical transformation, which are my x values. So I multiply those by 1/2. So I'll have 1/2, 0, -1/2, 0, and 1/2. So for this one, that 3 out front is a vertical stretch, meaning I'm going to make the graph tall and skinny. Vertical meaning y values. So I'm going to take my cosine parent function, put that here, and I'm going to end up multiplying my y values times 3. So my x values stay the same. And I have 3, 0, -3, 0, 3. All right, onto the graph. I need to make my graph go out to 2 pi. So if I do 3, I can get this will be pi over 2. This is pi, 3 pi over 2, and 2 pi. And I need my y values to go up to 3 and down to -3. So I'm just going to have to go by ones here. So this is 1, 2, 3, and then -1, -2, -3. So for my first graph, at 0, I'm going to be at 1/2. At pi over 2, I'm at 0. At pi, I'm at -1/2. At 3 pi over 2, I'm at 0. And at 2 pi, I'm at 1/2. So if I was going to sketch this, it still has that curve shape. It has just been shrunk by a factor of 1/2. Because if I'm going to graph my parent function, which I'll do in orange here, my parent function is going to be this, which is going to also look like we've condensed it, but it's just because we've changed the window that we're viewing it in. So orange is my parent, I'll call that P of x. And then my last one, at 0, it's at 3. At pi over 2, it's at 0. At pi, it's at -3, 0, and 3. And again, I want to make sure that it's coming from the bottom and not going above the value of 1. And there is y is equal to 3 cosine of x. So notice that one is way taller and stretched out from the orange one, whereas the green one is crunched a little bit. So that would be my vertical stretch versus my vertical shrink. Next up, we have a horizontal stretch or shrink. And so they give us these two graphs. They give us y is equal to sine of x over 2 and y is equal to sine of x. So y is equal to sine of x, that's just my parent function. But you can see here y is equal to 1/2 sine, or y is equal to x over 2. Those are the same thing. Dividing by 2 is the same thing as multiplying by half. Means I go back up here and I look, okay, that's a horizontal stretch or shrink. I go back and realize that because it's between 0 and 1, it's 1/2, it's going to be a stretch. So I end up multiplying my x values by 2. And when I do that, 0 stays as 0, pi over 2 becomes pi, pi becomes 2 pi, 3 pi over 2 becomes 3 pi, and 2 pi becomes 4 pi. I end up with my y value staying the same, and I get a stretch. You can see that where 1 normally would take place, we only saw a half. Notice what was our stretch shrink factor here, and it actually takes twice as long for us to see one full period of the transform graph. In that time, I see 2 full parent functions. When you have these translations, we can find the endpoints of the graph by finding the period and then using the following equations. Given the graph y is equal to a sine of bx minus c, those are all your transformations. The starting point is bx minus c equals 0, and the endpoint is bx minus c equals 2 pi. Next up is this example where we have y equals 1/2 sine of x minus pi over 3. You can see I started by diagnosing what are my transformations, and the 1/2 out front represents a vertical shrink, whereas the minus pi over 3 represents a horizontal shift to the right. So the shrink means I'm going to multiply my y values by 1/2, and then the shift means I'm going to add pi over 3 to my x values. So I start by writing out my sine parent function, and then I'm going to do one xy chart where I do y's times 1/2, and I'm going to do another xy chart where I do x's plus pi over 3. You can see my first xy chart, this one right here, I multiplied all my y values by 1/2. And then what happened when I add that pi over 3 is I need a common denominator. So what I did from this one to this one is I put everything in terms of pi over 6 because that's going to be my common denominator. And so then from the next two, I ended up adding pi over 3. Pi over 3 is really 2 pi over 6. I got a common denominator and then added 2 pi over 6. Now I'm going to move to the graph, and you can see I went carefully so that I could go all the way out to 14 pi over 6. That's my last x value, and so I'm going to plot these points. And when I plotted my xy values, this ends up being my final function.